Hello everyone, I'm Jenish Malla, a past Nepal TS giver, and today I'm taking a class on basics of functional equation. Today we'll just discuss the normal stuffs about functional equation. Normal equation is something like x plus y equals to 4 and x minus y equals to 2. But a functional equation is of something of the form x plus f of y equals to x plus 3. And in a normal equation, you solve for variables x and y, whereas in a functional equation, you solve for f. So I'll first go on over some basic definitions you'll need throughout this video, and furthermore, so some basic definitions are so function f is from a to v. This means a is the domain and v is its image. Like you can imagine it like this. Let's say there is set a and set b, a b c 1 2 3, and it goes a from 1, b to 2, and c to 3. Now our functions are of various type, and we go through them. Functions. The first type is injective function. Our injective function is, let's say, f of a equals to f of b. Then for the injective function, this will imply a equals to b. Now when solving any functional equation, what you can do is, let's say there's a functional equation f of x is equal to f of x plus f of y is equal to 3x plus 3. Then you say, let's take a and v such that f of a equals to f of b. Then if you can prove that a equals to b, then f is injective. Now what's the use of proving injectivity, you say? The useful of proving injectivity is, let's say you get an equation like f of x plus f of x is equal to f of 3 plus x. Then if f is injective, you can write f of x plus x is equal to 3 plus x, which will imply f of x is equal to 3. Now another useful definition is surjective, a surjective function. A function is surjective. Let's say a function f of a to v is surjective if f takes all the values of set b. Let's say f is from R to R, then f of x can equal any value from R. Now if you prove f is surjective, then you can take f of y is equal to alpha of any choice. This can be 1 0 or anything. But if f is not surjective, then you cannot take f of y is equal to alpha, because you have no proof that alpha exists for a given y. And one helpful thing after proving surjectivity is taking f of alpha so that it equals 0. We can use it for many equations. And second thing is bijective function. A function is bijective if it is both injective and surjective. And this and involution. This is the last definition. Function is called an involution if f of x equals x, and if function f is a involution, then it follows that f is also a bijection. Now let's move on to how to solve functional equations. Functional equations. So there are three major techniques of solving a functional equation. One is substitution. Let's say for a simple example, f of x plus 2 is equal to x plus 4. Then we can take x is equal to y minus 2 to give f of y is equal to y plus 2. And this is a solved functional equation. And generally, this is like the major substitution strategy. In substitution, you can take, let's say, a functional equation f from R to R, such that f of x plus y is equal to x square minus y square. Then here are the following substitution you can take. For, let's say, you can take x is equal to f of x also, y is equal to f of y. But the inverse you may or may not be able to take. For example, you cannot take f of x is equal to alpha unless f is surjective. And then while writing your functional equations solution, you can do this. You can say let p x comma y be the assertion. So what this basically means is that, let's say you want to substitute x is equal to 0 and y equals to f of x. Then instead of writing this all, you can just write e 0 comma f of x implies f of 0 plus f of x is equal to 0 square minus f of x whole square. Okay, now the next strategy is our applying involutions. Involutions. Let's say we are given f of x is equal to x plus 2. Then we can have f of x is equal to f of x plus 2. This is basically applying f on both sides. And also, if you take p p f of x, you can get f of x is equal to f of x plus 2, which implies f of x plus 2 is equal to f of x plus 2. Another useful strategy is looking for isolated terms. Looking for isolated terms. So what are isolated terms, you might say? Let's say there is a functional equation f of x plus y is equal to x square, f of x square plus y. And the term y is called the isolated term, basically because it is not inside a function. Now, isolated terms are almost necessary to prove injectivity. Necessary to prove injectivity, and also for subjectivity and surjectivity. So when you prove surjectivity, you basically want to show that f of something equals to a free variable x plus any constant, and this constant can also be 0. Basically what's going on here is that the RHS is surjective, which will mean that the LHS is also surjective, and since LHS is a function, that means f is surjective. And our third strategy is looking for asymmetricity. So I'll give a proper example for this. Let's say we have a function f of x plus f of y equals plus f of x y equals to f of x plus 1 f of y plus 1 minus 1. So what we can see here is that the function is relatively symmetric. That means if we say p y comma x, that is basically changing x to y and y to x, we get f of y plus f of x plus f of yx is equal to f of y plus 1 f of x plus 1 minus 1. And you can see that RHS and LHS are equal in both, so we can just write f of x plus f of y plus f of yx equals to f of y plus f of x plus f of yx, and this is basically the same, so we can cancel this out. And if f is injective, we can write x plus f of y is equal to y plus f of x, and by substituting p x comma 0, we have x plus f of 0 equals to f of x, which is our solution. And also, after you get the solution, you have to verify it, otherwise you risk losing 1 point. So to verify it, we can just write the original equation f of x plus f of y plus f of xy equals to f of x plus 1 f of y plus 1 minus 1. Then we put f of x is equal to x plus f of 0. That means we write f of x plus y plus f of 0 plus xy plus f of 0 is equal to x plus 1 plus f of 0 times y plus 1 plus f of 0 minus 1. And if you get LHS is equal to RHS, then our solution is a valid solution. Okay, now we'll solve some one question from Iran TST, a team selection test of 1996. So the question is to find f from real numbers to real numbers such that f of x square plus y equals to f of x minus y plus 4 times f of x times y. So here, before writing your before going for a solution, you should always try to guess the solution. So here, if you observe, then f of x is equal to 0 is a valid solution. And if you observe a little more, f of x is equal to x squared is also a valid solution. So you have to remember this solution when you are trying to solve this equation now. So to write the formal solution, we write like this: solution. Let Ex comma y be our assertion. Be our assertion. Now we just substitute. Now we do this. Px comma f of x implies f of x squared plus f of x is equal to f of x minus f of x plus 4 f of x times f of x, and which implies f of x squared plus f of x is equal to f of 0 plus 4 times f of x squared. Let's call this equation y. And now let's have another assertion px comma minus x. And the motivation behind this assertion is to make our LHS 0. Make this LHS 0. So we can write x squared. F of 0 equals to f of x minus x squared plus 4 f of x times minus x squared, which implies that f of x plus x squared is equal to 4 f of x squared. Now if you see the LHS here and here is equal, so these two must also be equal. Thus we write 4 f of x plus plus 0. So we write 4 f of x squared plus f of 0 equals to f of 0 plus 4 f of x whole square. Then we can cancel these two out, and 4 and 4 gets cancelled. Or f of x times x square minus f of x whole square equals to 0. Or f of x square minus f of x is equal to 0, which implies f of x is equal to 0 and f of x is equal to x squared. Now we are not done here, so we write verifying the solution, the solution for f of x is equal to 0, LHS is equal to RHS is equal to 0, and f of x is equal to x square. We also have LHS is equal to RHS. For you have to sort by putting the values, but for now, for convenience sake, I have left this out as an exercise, you could say. Now for after this also we have to, so we have to go through a process called point wise trap, which is beyond the scope of this session. So I'll go through this in the next session. So we'll do another question. F of x plus y, f of x minus y is equal to x plus f of x square minus y square. If you look at this question and like take some time to guess the answer, you can see that f of x is equal to x plus 1 is a valid solution. So now we try to prove this. Now we try to obtain this and other possible solutions. So let p x comma y be our assertion. Then we substitute p x comma x, and we can get f of 2x. F of 0 is equal to 2x plus f of 0. Now if we substitute p 0 comma 0, we can get f of 0 whole square is equal to f of 0, or f of 0 whole square minus f of 0 is equal to 0, which implies f of 0 is equal to 0 or 1. Now let's say f of 0 is equal to 0. In this equation, from this equation we get 0 is equal to 2x, which implies x is equal to 0. Therefore, f of 0 is equal to 0 is a valid solution only if x is equal to 0, but our function is defined from from R to R. So since this does not obey our entire domain, with our entire domain of real numbers, we cannot take this as a valid solution. So now we take for f of 0 equals to 1 from this same equation, we get f of 2x is equal to 2x plus 1, and then we let 2x is equal to y, and then we get f of y is equal to y plus 1, which is basically f of x is equal to x plus 1, x plus 1. Now if we substitute f of x is equal to x plus 1 in our original equation, we get something like this. We get x plus y plus 1, x minus y plus 1 is equal to 2x plus x square minus y square plus 1, or this is basically x plus y plus 1, x minus y plus 1 is equal to x square plus 2x minus y square plus 1, and this is basically a plus b, a minus b, so x plus, oh shit, this is x plus 1 plus y, x plus 1 minus y, so this is x plus 1 whole square minus y square is equal to x square plus 2x minus y square plus 1, or x square plus 2x minus y square plus 1 is equal to x square plus 2x minus y square plus 1 2. Therefore f of x is equal to x plus 1 is a valid solution, and we are done. So this is all for our first lecture. In the second lecture, I'll discuss about pointwise strap and Cauchy's functional equation. So the lecture handout of this lecture is in the description below. You should try to check it out, and I have given 3 problems for you to try, which are almost, let's say, which are solved by all the knowledge I have given over here. Thank you.